Hi, physics students. Today we're going to talk about sound intensity and resonance. So, um, when we talk about intensity, we're talking about talking about how loud a sound is, but it's not really the same as that. Intensity is actually it's an objective measure of the power per unit area of a particular sound wave. And you can see the equation right here. I stands for intensity, P is power, and again, power is the rate at which you're doing work. Um, and then 4 pi r squared is the area of the surface area of a sphere. All right, and because it's power, it's measured in watts, and area is measured in meters squared. Uh, and we refer to intensity as loudness, although they're not exactly the same thing because loudness is a human perception of a given intensity. If you're watching TV and you think that the volume is too loud and someone else thinks it's just right, the TV isn't doing anything different to each of you. It's just you're interpreting it differently, and it's just based on your own hearing. Right here, I've got a graph, and this kind of shows what we are able to hear. The other day, I talked about how we have a range of frequencies that we can hear. We can hear between 20 hertz, which is on the very low end of frequencies, and then up to 20,000 hertz, which is like the best human or the highest note a human can hear. Most humans kind of lose their hearing around 16,000 hertz. But in addition to frequency, there also has to be a given intensity. If a sound is too quiet, it doesn't matter what the frequency is, you're not going to hear it. So this is a graph that shows frequency versus intensity. And so you can see here's 20 hertz. That's the lowest sound a human could hear. But again, if it's not intense enough, you're not going to hear it. You have to have a really intense sound, and here they're showing intensity in terms of decibels. You have to be up in the range of 100 to 120 decibels, and that is really loud sound. Sounds that are in the 120 decibel range are like jet engines, rock concerts, stadiums full of people cheering. That's You're not going to hear a 20 hertz sound much lower than that. When we talk, most of our speech is in between 100 hertz and about 8,000 hertz. And again, those intense sound intensity levels are, between 40 and 80. Music expands on that because there are other notes that can be played, pitches that we hear. And again, we listen to music a little bit differently than we listen to people talking. And then this whole area out here, this kind of lighter pink, is just all the other ambient sounds that we hear during the day: construction, traffic, leaves rustling, all those different types of things. But you can see again that at lower frequencies here, you need much more intense sounds to be able to hear them. If a sound is higher, it is easier to hear at very low intensities. Relative intensity. So this is what we refer to as loudness, and we measure this in decibels. So again, here are intensities, and here are the decibel ratings that we give them. Now, the decibel scale is a logarithmic scale. Every step up is of 10 decibels is 10 times as intense. So the lowest, the sound you can't hear is measured at 0 decibels. Something like leaves rustling, that's very quiet. That's 10 decibels. But look, it's 10 times as intense. There's 10 times more power in that sound. Now, if I go up 10 decibels up to 20 decibels, I've now increased by another power of 10. So this is 100 times more intense than, that threshold of hearing. Let's, go down here. Think of a vacuum cleaner, 70 decibels, 1 times 10 to the minus fifth watts per meter squared. If I go up to 100 decibels, that's 30 decibels, and you're like, oh, that's not that much more. But really, it's 10 times 10 times 10. That's 1,000 times more intense on your hearing. In this power motor, a subway, train station, way more intense than a vacuum cleaner. Vacuum cleaners can be pretty loud. So jet planes, these are in those areas of what we call the threshold of pain. And you can actually break an eardrum. You can have bleeding from the ears that sounds above that. This is just another one. Kind of goes through the same thing. But the main thing you want to remember here is that the decibel chart is logarithmic. All right, so how do we hear things? You've heard of your eardrum. Some of you are taking anatomy right now. The technical name for your eardrum is a tympanic membrane. There are three tiny little bones. They're referred to as the anvil, hammer, and stirrup based on their shapes. They're three smallest bones in your body. They have actual real names, but I don't remember what they are. And so when that membrane vibrates, and it's super sensitive, it can, we're talking fractions of a millimeter that it will vibrate. Well, when it does that, it pushes on these bones, which then activate the cochlea, and that is with your inner ear, and that's going to send electrochemical impulses to your brain, and then your brain interprets what those sounds mean. When you're born, you don't know what sounds mean, but you start to attach particular sounds to particular events and names and those sorts of things. All right, we're going to skip ahead here and from harmonics and beats, and we're just going to go to resonance and forced vibrations. All right. So if you vibrate, if I take two pieces of wood and I clack them together, they create a vibration. And if that vibration is at a given frequency, and there are two other pieces of wood nearby that are, if they start, that can cause them to start vibrating at that same resonance. Now, you're not going to see that really in something like wood, but if you have two different tuning forks, you can do that. If you have two guitars next to each other, if you play one note on a guitar, you can cause the other string, or the same string on the other guitar, to vibrate, and that's called forced vibration, and we also call that resonance. Now, lots of different things have their own particular natural frequency at which they will resonate, which means that the standing waves will just keep building and building until the waves get so big that they can cause damage. You can go ahead and watch this video of them shattering a glass. Oops. That video is unavailable. Well, that's the Tacoma Narrows Bridge. So if you want to see that, I'll fix this in the notes. But if you want to see it, just type in Tacoma Narrows Bridge, and it'll show a bridge that collapses because of that. And then finally, beats. When you strike say, for example, a tuning fork, and it rings out, and then you strike another tuning fork that is the same, that's almost the same frequency, they will mesh into a sound, but it's going to get louder and softer. It's going to wah, 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 kind of like that. And those wah-wahs are what we call beats. Now, the number of beats that you have per second will tell you how many hertz difference you have in frequency between the two tuning forks. So if you have one tuning fork at 259 and one tuning fork at 263, and you strike them both, you should hear 4 wah-wah-wahs every second. This graph right here is an example of kind of what happens, how the waves superpose. If I take this wave and I take this wave and I add them together, what you get are the green waves. So sometimes the crests line up and you get constructive interference. Sometimes the crests don't, crests and troughs line up. So here I've got a crest on this red wave. Here I've got a trough on the blue wave. So on the green wave right here, you can see that there is no amplitude. But then they slowly start to, get in phase with each other. And so then we're back here to this situation where I have a crest and a crest that superpose, they constructively interfere, and now I have a huge wave. And so each one of these wave structures is what we call a beat. And so it'd be wah, 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 kind of like that. Obviously much faster than that. Okay, that is all.